First student I can see Himan Ash. Himan,
So,
you are getting what I'm discussing these days?
yes, sir.
Do you go through the lecture after the class?
Yes, yes, sir.
Okay, very good, very good. Pawanjot Singh, what about you?
Yes, sir.
Very good. Madhu Beniwal,
Yes, sir.
okay, you are getting what we are discussing?
Yes, sir, but sometimes I got difficulty. Then I watch your recorded lectures. Then,
Okay. I am giving my copy of my class notes, so you should not feel that we will read any time and just relax. I am giving these notes so that you need not to note down during the lecture and concentrate only on understanding.
yes, sir. Yes, sir.
Hmm.
Yes, sir.
So sometimes it may be negative that you may feel that okay, we will read it at our leisure time and we will may not be concentrating in the class. Okay. So now if there is no difficulty, so let us start. Okay. So let me share this screen. Share this screen.
There was a difficulty in the question from tute sheet actually.
Uh-huh.
The
Just a
sixth
moment.
question.
Mhm. What
Uh,
are you seeing on your screen, by the way?
yes, sir, your screen is visible.
What are you seeing on the screen now?
MS Teams, sir.
L-
Team.
MS
lectures.
lecture you are seeing. Which page number?
Sir, it's not a
Yes,
page
we are
number,
seeing
it's
Teams
scheduling
page.
a lecture.
Okay, okay, let me see. So what are you seeing on the screen now?
Example 1, sir.
Page 57?
Yes, sir. 57.
Okay, right. Now let me come to your difficulty. So what is your difficulty? Tell me.
So in the tute sheet,
Uh-huh.
we couldn't get the answer of question 6.
Question 6. Let me see tutorial sheet question 6. Okay. Question 6. Okay. A plane wave in electromagnetic waves incident at the input end of a symmetric planar optical waveguide. If its electric field is described by this plane wave, K being the free space obtain the amplitude of the TE0 mode. So do you remember how have you tried to do this question? Did you try?
So in this, what we used is like you taught an excitation of guided modes.
Yeah.
So we did amplitude is equal to integral of
Mm-hmm.
incident field
Mm-hmm.
into conjugate of electric field.
Right.
So,
So,
but we couldn't get the answer right. We did the normalization thing also, like you told that we do normalization of
mm-hmm.
electric field to get the delta thing, the
Mm.
one.
Right.
So for that, like in example fifth A, tute sheets question fifth A, the same
Mm-hmm.
thing is done that for normalization we have to find A. So we
Right.
use that A amplitude.
Mm-hmm.
Even then we couldn't get the answer right.
So what is your integral then? When you take the overlap integral, what is the integral? I think what I will do, I will then write down on a piece of paper and then show you, right?
Okay, sir. Sir,
Ah.
in this, can you please tell me? I followed your lecture, but I couldn't get one point in this concept that we write that incident field is equal to summation of all the fields multiplied by some AM.
Some AM.
Yes, sir. On
Which
page
is
26.
on page
26.
26. No, what we are saying is on page 26, right? So incident field on the waveguide and is phi of x, right?
Yes, sir.
Now this will couple energy optical waveguide,
Yes, sir.
and that energy, that field would be coupled either to the guided modes or radiation modes.
Yes, sir.
So if AM is the amplitude of mth guided mode, then the total field of the guided modes would be summation AM psi m of x.
So this is the question that why we have taken AM as amplitude separately, because in phi m already there is amplitude.
No, that amplitude is not known by that. See, when you write down the modal field pattern, you write down, say, for example, planar waveguide, say, some constant A cosine kappa x in the core, exponential minus gamma x in the cladding. But that is unknown, right?
Yes, sir.
And that suppose you have selected, let me say you have normalized the wave function. So you will get A is equal to the, for example, this in question number 5, I have given you the what would be the amplitude. That would be
Yes.
1 upon under root A plus 1 by gamma, right?
Yes, sir. Yes,
So now
sir.
this is the field.
Yes,
So
sir.
this is this constant I have selected in the sense and to normalize it, right?
Yes,
But
sir.
how much energy would be coupled to this mode, that would be decided by AM. So
Okay, sir. We can
for
see
example, if you don't launch the light, then what would be the amplitude of this mode excited?
so then it would be simply A into cos kappa.
Then there is no light coupled by, there is no
Okay, no
question of
light.
amplitude.
Okay,
I
so
am
then
asking you, when you launch light into the waveguide, suppose I don't launch any light.
okay,
So
sir.
what would be the amplitude of the mode excited in the waveguide? When the mode
There
is
will be
not excited, the amplitude will
yes,
be zero.
yes, sir.
So this AM is that amplitude, right?
So we can compare it that these are the weights that will be assigned to different modes.
Weight, what do you mean by weight? Right? I do not.
So we want to say that these are the factors that will be that it will be further multiplied due to the
See,
input field.
that amplitude which I had discussed is during the solution A cosine kappa x, that you can take anything. A can you can take 1, 2, 3, 4, 5, infinity, whatever you like.
Okay, sir.
Just to make sure that everybody select in the same way, we normalize it.
Yes, sir.
So that is just normalization factor. But now how much of this field would be excited, that is decided by AM.
Okay, sir. Yes, sir.
Sir, then AM will be numbers. It will be dimensionless.
Yeah, it would be number, of course. Of course, it would be number.
So when we will solve this, we should uh, we are not getting the answer. Then we will follow your
Okay,
answer and you will send that.
you must be taking maybe, okay, I will solve it and then display to you, right?
Thank you so much, sir.
Any other question? Okay, so what are you seeing on your screen now?
Page 57.
Page 57. So we will start from here. Good. So let me come to this slide. And here is the slide. Okay. Right, I do. So everybody is seeing.
Sir.
Okay. So last time, what we discussed is the following. So we were discussing this. Just a moment. Yeah. Intermodal dispersion in general graded index fibers, right? And what we had discussed last time, that we have a optimized profile for which q is equal to 2 minus 2 delta, and for that the intermodal dispersion is minimum. And that's what I discussed, that how the communication system they progressed, and the development in improvement in the communication system that came basically because of all this theoretical analysis. So for example, initially when step index fiber were developed, and I had given you the numerical values last time, that intermodal dispersion was too much. And so nobody was really bothered about material dispersion or anything else. And it was found that it would be not a very economic thing to use step index fiber. Then people thought how to, and that was intermodal dispersion. Then people started working on theory, and they tried to find out the solution for this, tried to reduce intermodal dispersion, and they came, finally solution came in terms of this graded index fiber. And then we had discussed that intermodal dispersion is decreased a lot. And then in near parabolic fibers, material dispersion became more than intermodal dispersion. So the repeater spacing, or how many bits per second you can communicate, was decided by the material dispersion. The first generation communication system, they use near parabolic multimode fibers, and repeater spacing was something like 12 kilometer. At that wavelength, the wavelength was used 0.85 nano micron. Loss was about 3 dB per kilometer, and about bit rate 45 megabit per second could be transmitted. Then since material dispersion was dominating, so people thought how to decrease the material dispersion. And they found that material dispersion is minimum around, for silica, around 1.27 micron. So they thought if we could get this, source at that wavelength, that would be very good. So so semiconductor technology was somehow progressing very well, and we could get sources at 1.3. So in second generation communication system in 1981, multimode fibers, near parabolic fibers, core fiber, multimode fibers, around 1 lambda is equal to 1.3 micron were operated. And then the repeater spacing could be increased to 30 kilometer from 12 kilometer, but typical bit rate was still 45 megabit per second. Then loss was about 1 dB per kilometer. Fortunately, at 1.3 also loss was much less as compared to 0.85 micron. So that was a very good solution. But then again, and then intermodal dispersion started dominating, because material dispersion is very, very small. Then intermodal dispersion started dominating. Then people again thought the solution, that what is the solution if we want to further increase the information carrying capacity. And the solution came that if we can altogether remove the intermodal dispersion, that is, if only one mode is permitted to propagate through the fiber, and that we have already discussed, that if you select the parameters of the fiber in such a way that V is less than 2.4048 in step index fiber, and value you can out in parabolic core fiber. So then you can have only just one mode actually. So no question of intermodal dispersion. So then people started developing single mode fiber, and in the third generation communication system around 1989, single mode fibers were used at 1.3 micron. And then the bit rate was increased to 500 megabytes per second from 45 megabit per second, and repeater spacing was increased to 40 kilometer. Losses were less than 1 dB per kilometer. So this was a very good solution. But don't think that around, I mean, when material dispersion is zero, that dispersion is not there. Still, there is some dispersion there. And today we will discuss what is how do we calculate dispersion in single mode fibers. And the dispersion is known as intramodal dispersion. That is dispersion within the mode itself. And I had discussed earlier also that this is because of the finite bandwidth of the pulse, because each pulse has different wavelengths propagating in the pulse, and these different wavelengths, they travel different with different velocities, take different times to reach at the output end, and hence you get a pulse broadening. And this pulse broadening, in a simple way, you can, although, I mean, to find out the exact pulse broadening, I should take the shape of the pulse also into account. But right now we are trying to get an estimate. So we assume, suppose a impulse, I mean, delta pulse is launched at the input end, then what would be the pulse broadening like? So suppose t is the time taken by wavelength lambda. So we calculate the dt by d lambda, rate of change of time with respect to lambda, and multiply by the bandwidth. So that would be the pulse broadening. And I am not repeating, I have shown you in one of my lectures that this is minus L by C lambda d square and effective by d lambda square delta lambda. Now these parameters L and delta lambda, they are the characteristics of either the fiber length, how much fiber you take, or what is your source. So this is not related with the fiber actually. So what we define dispersion, pulse broadening per unit length of the fiber, per unit bandwidth of pulse. And that comes out to be lambda by C d square and effective by d lambda square. So when we compare different fibers, we compare their dispersion coefficient, because you can always take different lengths. So that is not a that should not come into the comparison of performance of different fibers. So now where from this dispersion comes? So this dispersion comes basically because group velocity of different wavelengths at different wavelength is different, and that comes from the two factors actually. First, even if you consider is homogeneously infinite extended medium, the refractive index depends on wavelength. So you will get different group velocities for different wavelength, and you will get pulse broadening. So that contribution that is known as material dispersion. We denoted that coefficient dm. But there is another factor, that even if I assume that somehow I have both the materials N1 and N2 and their refractive indices do not depend on wavelength. But because of the waveguide nature, because V parameter for different wavelength is different, so the propagation constant would be different, and so the group velocity would be different. So because of this waveguide nature of the structure, that we get dispersion here. So that contribution comes waveguide dispersion. So today we will try to understand the contributions of material and waveguide dispersion, relative contribution, and we will see if we can further improve the performance of the fiber by playing with these dispersion, these two contributions. So for example, material dispersion, actually we cannot do much, because once we have selected the fiber material, and silica is the found to be the best and cheapest material available. So for this silica, now single mode fiber, for example, most of the power, say I would say 90% of the modal power propagates through the core. So in order to have an estimate of the material dispersion, let me assume that my n effective is roughly the refractive index of the curve, this here. So dm would be minus lambda by c d square n by d lambda square. This n1 is silica refractive index. And I had told you this earlier also, that if you calculate that, this data is available in the books, and you can find out that at different wavelength, I have considered here 3 different wavelengths: 0.85 micron, because the first generation fibers used this wavelength, and then 1.3 micron, because at this the material dispersion is almost 0, and another wavelength of interest is 1.5 micron. I will come to this point, why this is interesting wavelength. So this is interesting basically because at 1.55 micron, the loss is the minimum possible loss you can achieve in a fiber. That is 0.1 dB, 18 dB per kilometer. And fortunately then, because loss is so small, and even that loss can be compensated using fiber optic amplifier, erbium doped fiber amplifiers, which operates at 1.55 micron. So that is a very good coincidence that at that wavelength we can have fiber amplifiers also, and at the same time your loss is very small. So the next thing to improve is that if we can shift the zero, this total dispersion, if we can make 0 at about 1.55, then nothing like that, because at that point loss is minimum. Then if you can shift this wavelength where the total dispersion is 0 at 1.55, so this dispersion would be small, and so it would now the spacing would be decided by the loss. In basically, in fact, dispersion is almost 0, and then that loss can also be compensated using fiber optic amplifier. So you will get almost, I mean, unlimited bandwidth actually. So that is the dream actually. So, and it is realized now. So let me come to the, so material dispersion we cannot do much. That is fixed by the material. So let us look at the waveguide dispersion. So I will take, just to get analytical results, I will take certain approximations, but these approximations are quite okay, quite fine. So for waveguide dispersion, actually I want to know, I have to, whether it is waveguide or material, basically I have to find out n effective, right? So let me put, first of all, this normalized propagation constant, which is defined like this. If you remember our discussion on step index fiber, for example, so B is a function of only V parameter. The eigenvalue equation, if you remember, the solutions of the eigenvalue equation, for example, fundamental mode, that is, if I remember correctly, it was J0, J1 by J0. Anyway, I don't remember the eigenvalue equation right now. But once V parameter is fixed, B is fixed. So I will try to put everything in terms of B, because once V parameter is fixed, so then you have standard result, universal results, which give you the value of B. So B is defined like this, and since generally N1 and very close to N2, so beta by K naught for guided mode, because it is lying between N1 and N2. So I can approximate it like this. So beta by K naught plus N2 would be roughly N1 plus N2. So this would be approximated like this. And from this relation, if you calculate n effective, you can write down N2 plus N1 minus N2B, and which would be roughly, if I divide it by N2 multiplied by numerator N2, N2 you can take outside 1 plus delta B. So this is how you can approximate the n effective of a single mode fiber, right? So next I have to find out the second derivative of n effective. So, and remember, I am calculating waveguide dispersion. So I am not considering now the wavelength dependence of N2 or delta. So I am material dispersion I have considered separately. So if you assume that N2 and delta are not wavelength dependent, then the first derivative, it's very simple calculation. So you put n effective from here, and this would be N2 delta minus, this is d by d lambda of B, but V is related with lambda like this, and you can show that dv d lambda is minus v by lambda. So this operator d by d lambda is nothing but minus v by lambda d by dv. So I want to put everything in terms of v. So I put this operator d by d lambda in terms of d by dv. So this is what you will get. And the second derivative again, and I have shown you the steps here, and you can, if you want, you can go through it. I can also go through it. So second derivative from this equation, from here, minus n2 delta d by d lambda of this. So I can, this is minus v by lambda square d by dv of v plus 1 by lambda d by d lambda of v d by d lambda I substitute from here, minus v by lambda by d by dv. So you will get this step and this step. Finally, you can put this in the very compact form. So dw comes out to be minus n2 delta by c lambda v d square by dv square of vb. So this is how you can find out the contribution from waveguide dispersion. So although in principle I should solve the eigenvalue equation, but let me tell you, when you solve the eigenvalue equation, you find out b as a function of v. So the exact technique would be to solve the eigenvalue equation taking the refractive index, wavelength dependence of refractive indices n1 and n2 into account, and find out b as a function of v, and then find out that will give in fact the total dispersion, and then find out d square by d lambda square of an effective. But now we are trying to find out their contribution separately. So in this expression I have forgot removed, I have not considered the wavelength dependence of n2 and delta, and this is what will come out. Now further, people have simplified this calculation by proposing a empirical relation of B, and B can be, V dependence of V can be approximated by this simple relation, and this relation is very good approximation. If you can see in the probably it is within 0.01%. It gives the values of V for a given V in this range V, and we never go beyond this range. In fact, when we use single mode fiber, generally we use V parameter around 2 or 2 to 2.2, something like that. So this is a very good approximation to have a idea that what is the waveguide dispersion. So see what I require in this. So to calculate dw, I require second derivative with respect to v of v times b. So if b is given by this, v of b, v times b would be given by this. First derivative if you calculate, so derivative of this function, and this is quantity itself, plus then v as it is, and differential of this 2 times this bracket, and then differential minus b by v, which is b by v square, and this will come out very simple. This will be simplified to a square minus b square by v square. And now if you take the second derivative, because here I require second derivative of vb, and second derivative comes out very simple form, that is twice b square v cube. And now if I put this d square by dv square of vb in this equation, dw, then what you get is the following. So the waveguide dispersion comes out to be minus n2 delta by c lambda v, and this is the value which I have just calculated, twice v square by v cube. So one v cancels and you get this, and by definition v square is equal to k naught square a square n1 square minus n2 square, and which is n1 square minus n2 square can be written down as n2 square into 2 delta. This we had discussed several times. And dw in terms of wavelength, etc., that becomes like this. So now I would like you to concentrate on this expression. Waveguide dispersion coefficient is given by minus lambda upon a square b square 4 pi square n2c. So at any wavelength, you can see the waveguide dispersion can be tailored by selecting the value of a. B is constant, n2 is almost constant, lambda is given. So at any wavelength, you can now play with the waveguide dispersion by selecting appropriate value of a. If you decrease a, waveguide dispersion would increase. And if you increase a, waveguide dispersion would decrease. And total dispersion is dm plus dw. So now this gives an idea that you can make total dispersion 0 at any desired wavelength by selecting the value of a appropriately. And let me show you that is, if you plot typically this waveguide dispersion and material dispersion. So in this figure I have plotted schematically the dispersion coefficient of due to material. So it is negative below 1.27 and positive. Remember, dm is minus lambda by c d square n effective by d square n1 by d lambda square, and d square n by d lambda curve was like this. So that by changing sign, the dispersion coefficient would be negative below 1.27 and positive above 1.27. And now if you plot the waveguide dispersion, that is always negative, but its magnitude depends on A. So typically it is like this, right? So maybe I could not draw this line correctly, because so normal at conventional fiber, this total dispersion is something like this, becoming 0 around 1.3. I should have plotted this line slightly like this, so that this material dispersion is exactly cancelled with waveguide dispersion around this wavelength. Anyway, this is just a schematic figure. And see, if you decrease A further, then this waveguide dispersion would come down and down. And you can see the sum of the material dispersion and waveguide dispersion would be 0 at some higher wavelength. So this is the idea, that you can make a total dispersion 0 at any desired wavelength, right? So I have taken a few examples here to show you that how you can tailor this total dispersion. So for example, if I take lambda is equal to 0.8 micron, so this is this you can get from handbooks. D square n by d lambda square for silica is about 4 into 10 to the power minus 2 micrometer minus 2. And if you calculate dm, simple calculation, you will get minus 100 picosecond per kilometer nanometer. And now let me find out the waveguide dispersion. So I have selected here the parameters of the fiber such that at lambda is equal to 1.8, my V parameter is roughly 1.9. So A is selected 3 micron, delta 0.0. These examples are given in optical electronics by Professor Ghatak and Tyagarajan. So I have taken those examples from here, actually, these examples from there. So N2 is 0.45. So dW comes out to be minus 5 picosecond per nanometer kilometer. So the total dispersion would be minus 105 picosecond per kilometer nanometer. But now I will take another example to show you that you can select the fiber parameters. You can get total dispersion something different. So for example, 0.3. Second derivative of refractive index is about minus 5.5, 10 to the power minus 4 micrometer minus 2. And if you calculate material dispersion, comes out to be 2.4 picosecond per kilometer nanometer. And now I can select the fiber parameter in such a way that my dispersion becomes 0 at 1.3 micron. And that is true if I select A is equal to 5.6 micron, delta I select 0.00117, N2 of course is roughly 1.45. So again I get V parameter as 1.9 and this at wavelength lambda 1.3 micron. And if you calculate waveguide dispersion, then you get it is minus 2.4 picosecond. So material dispersion is plus 2.4 picosecond, waveguide dispersion is minus 2.4 picosecond per kilometer nanometer. So the total dispersion becomes 0 at 1.3, resulting in a very large bandwidth. Now remember, when I say that total dispersion is equal to 0, coefficient is equal to 0, it does not mean that the total pulse is 0. The reason is that you are working around 1.3 and your pulse has a finite bandwidth. So you would have wavelength on both sides of 1.3 where the dispersion coefficient is not equal to 0. So you will still get some broadening. So, but anyway, at this particular wavelength, total dispersion. So around if my carrier frequency is around 1.3, so those pulses generated around 1.3 carrier frequency, they would have extremely low dispersion, and this will result in a very large band. So I have some points to be appreciated, that systems operated at 1.3 is now limited by loss because dispersion is 0. So you can go to very large lengths. The only limiting factor would be then loss, because after a certain distance, if the loss is too high and your intensity of the pulse is so low that you are unable to detect it, that would be a limitation. Now, since loss is minimum around 1.55 micron, it is attractive to shift the zero dispersion wavelength. By the way, this wavelength at which the total dispersion, sum of material and waveguide dispersion is 0, that is known as zero dispersion wavelength. So that is a standard terminology we use. So it is attractive to shift the zero dispersion wavelength to lambda is equal to 1.5. And this can be achieved by tailoring the waveguide dispersion accordingly. And select the fiber parameters in such a way that my total dispersion becomes 0 at 1.55. So that would be the best thing. So in that case, both dispersion and loss would be minimum, and you will get large repeater spacing. So here I have shown you a typical loss curve of a fiber, and so this is generally at 1.3 you have a low loss window, and we also have a low loss at 1.55. So people also, they always dream that if you can, that is possible. For example, in this last example I have shown you, at lambda is equal to 1.55 micron, second derivative of the 13 index for silica is minus 4.2 10 to the power minus 3 micrometer minus 2. And material dispersion comes out roughly 22 picosecond per kilometer. And you can always select the fiber parameter. I have given one example here, that if I select A is equal to 2.02 micron, delta 0.013, N2 is again, and I have selected this parameter in such a way that now the V parameter at 1.55 micron is 1.9. I am comparing the same fibers. In all the examples, V parameter I am taking 1.9. So dW comes out to be minus 22 picosecond for this. This you can do yourself because all the parameters are known. And so total dispersion now has become 0 at lambda is equal to 1.55. So by tailoring the waveguide dispersion, we have shifted the zero dispersion wavelength to 1.55 micron. Such fibers are known as dispersion shifted fibers. Those fibers which are laid down at around, which are optimized around 1.3 micron, they are known as conventional single mode fiber, CSF, conventional single mode fibers. And these fibers for which total dispersion is 0 at 1.55 micron, they are known as dispersion shifted fibers, DSF. So I would stop here today, and if there is any question, I will be happy to answer it. Otherwise, we will now focus on the quiz. So let me know if there is any problem up to this point. बोलो भाई, any question?
Yes, sir.
बोलो.
So, like while we taking the non-zero components,
Non-zero component means?
non non-zero components in TM mode or TE mode of like EX, EY, EZ.
By
So
now,
then
now there is no time for this discussion. I mean, today's lecture,
okay, sir.
now you should be ready for the quiz, right?
Okay, sir.
I take quiz on Tuesday so that if you have any difficulty, you can ask on Monday, right?
Okay, sir.
So let me now, and let me, I will be give, okay, let me first flash the quiz paper so that you can start. Okay, so let me come to this file. This is, I close this file here, and tutorial sheet, then quizzes, then quiz 3. What are you seeing on your screen?
We are seeing you actually.
Quiz not, you are not seeing the quiz?
No, sir.
No, sir.
No, sir.
What about now?
Yes, sir.
Yes, sir.
Okay,
No,
so I again repeating, you should write down your serial number, name and entry number. And don't write all the history in the quiz, right? This is just 2 marks question. You should not take more than 1 page. It is very difficult to combine all those pages actually. So whatever rough work, don't use this page for rough work. You just give me the, main steps, and just try to accommodate everything in one paper, 1 page, right? And I again repeat, the subject of the email and PDF file name should be your serial number underscore name, and you should submit it to these 2 emails, right? So start, and if you're any difficulty, confusion, you let me know. So you are given a planar waveguide, substrate refractive index 1.44, core refractive index 1.45, top index is air, you can take 1, total width is 2 micron, and what you have to find out that what is the wavelength range for which the waveguide would support only 1 TEG. By unmute yourself, there is some noise from somewhere.
Yes, sir. Okay.
By no talking and unmute yourself. Krishna Ballabh Kumar, you are not unmuted, bhai. So you are not muted. You, Sukhvinder, are you there?
Sir,
Yes.
sir, in question you mentioned symmetric planar waveguide and in figure it is asymmetric.
Yeah, whatever is given is given. Now, no question about that. Okay. Okay, I understand what you are saying. By mistake I written symmetric waveguide. So this is not symmetric. Yeah, you are right. I'm sorry, bhai.
सर ये प्रॉब्लम हो गई सर, मैंने पूरा वैसे सॉल्व कर दिया.
So we solved
Calculated.
according to symmetric.
You have
We
to
were
solve
according.
according to the figure. Whatever figure is given, you have to solve according to that.
Please
Okay.
give the time from now
Yes,
because we
actually, we have
solved
solved
and
that.
we were uploading.
I cannot expect you from, from you people like this, bhai. If I have written symmetric and the waveguide is given asymmetric, how can take it symmetric? What would you take? Would you take air below in the substrate region? So nothing doing. Whatever, you still have 10 minutes. If you can do it, so
Yes, sir,
so
thank you.
whatever figure is given, according to that figure, you have to find out. हेलो बोलिए।
हाँ जी सर, पोस्टमैन बोल रहा हूँ जी।
अच्छा हाँ भाई, क्या आ गया?
हाँ जी सर, दोनों पासपोर्ट आ गए।
अच्छा, तुम कब मिलोगे? मैं फिर यहाँ मैं आईआईटी के पास हूँ अभी, मुझे आप पहुँचने में थोड़ा टाइम लगेगा। तुम लंच पे कब मिलते हो?
पैसा ऊपर 11:30 12 तक लास्ट में मिलूंगा सर।
12 बजे तक? अच्छा। और
निकल जाते सर, फिर कल मिलूंगा जी आपको मॉर्निंग।
नहीं, फिर मुझे जरूर कल नहीं, फिर या तो फिर तुम हमारी सोसाइटी के गेट पे दे दो, मैं तुम्हारे से बाद में मिल लूंगा।
अरे कितने 271 वालों को लेके आना सर? वो क्या 271?
271 वालों को दे दो। हाँ
चलो ठीक है सर, मैं बात कर रहा हूँ।
हाँ हाँ हाँ, राइट। तुम अभी सोसाइटी में हो?
हाँ जी सर।
अच्छा, जरा बात करा दो फिर।
अभी आपका तो जनरल आएगा।
हाँ। हेलो, नमस्कार जी। वो नीचे से सोसाइटी से फोन आया होगा आपके पास, वो हमारे।
हाँ, जस्ट अभी आया है कि पासपोर्ट आया है आपका।
हाँ हाँ, तो आप कलेक्ट
रिसीव कर लेना।
हाँ,
ठीक है।
तो उसको अगर वो बंदा मिले ना तो उसको 100 रुपये दे देना हमारी तरफ से।
अच्छा
हाँ
ठीक है। अगर वो रुकेगा तो दे दूंगी, नहीं तो
ठीक है, ठीक है, राइट राइट। थैंक
वो ऊपर आ रहा है देने के लिए।
अच्छा, ठीक है,
अब फिर मैं आपको बता देती हूँ।
ठीक है, राइट। थैंक यू। चलो भाई, नाउ यू शुड वाइंड अप।
Sir, the second email is today is different. So we should send the PDF in that
No,
AQ.
is it different? Let me see.
Usually we send PDF in
AKSH.
Yes.
अच्छा, have I made a mistake again? Let me see. Okay, let me see what is it. Oh, I am sorry. Oh, this should be AKSH 8083 at gmail.com. Hello, everybody listening.
Sir, please repeat.
The first email address Sukhvinder is fine, but the second is AKSH 8083 at gmail.com. The same as you sent earlier, right?
Sir, previous one.
Previous one, yeah.
And sir, one more thing, the subject of email and PDF file, serial number and name. But yesterday you sent the email there. We have you said quiz number also. So I made the PDF that way.
Yeah, quiz number, if you put it in the last, there is no problem. First two should be serial number underscore your name.
Okay. Thank you, sir.
I have received Shivam, 18 Payal, 14 Antrish, 21 Akshay,
Sir,
29.
actually, I have. Hello, sir.
Hello.
I have solved using this, reading the question. I not considering the figure. Now I am solving again.
But you just get another 2 minutes. That's it.
Sir, have you obtained my mail? 53.
53, I am seeing AKSH 8083. 53 I have not received.
Sir, serial number 21, Akshay Tyagi.
21 I have received, 29, 31, then 53.
Sir, can we leave the meeting?
Yeah, you can leave the meeting. Yeah.
Thank you, sir.
53, 46, 32. $44.
The number 9.
Number 9, not yet. Have you
I have
sent
sent
it
it
to?
in 1952. One.
No. AKSH. Anyway, if you send Sukhvinder, that is fine.
Sir, 23 Dipanshu Yadav.
Have you sent to AKSH?
Yes, sir.
No, not
23,
yet.
23 Dipanshu Yadav.
20,
Serial number 23.
serial number 23, not yet. Maybe coming.
Sir, 48 Swasti.
48, no. Let me see. Okay, let me see again.
So please refresh it.
Okay. 46 I got, 32, 44, 40, 23 Dipanshu, 48.
Sir, 28.
28, yes.
Sir, 48. Have you got it?
Yeah, 48 I have got it. No, 48.
Okay, sir.
No, not yet. Let me see. Something. 20, 47, 48, yes.
Sir, 28 you got, sir?
28, yes.
The number 9.
9, yes. 47, Rushikesh, yes.
Sir, number 3.
Number 3, not yet. Number 22, yes. 49, 15, 26. Just a minute. Hello. अच्छा, thank you.
Mr. Dipanshu Yadav,
तो 100 रुपए में मान गया.
are you there?
चलो ठीक है. ठीक है. Thank you. हाँ.
Sukhvinder ma'am, have you got 48?
Yes.
Sukhvinder ma'am, I am Himan.
Yes.
Yeah, I
Yes.
have sent you 2 email because one is not going, so I think. Have you received it?
Okay. Himan. Yes, I got your mail.
So 2 mail actually.
I got only
Ma'am, have you
one.
got 49? Siddhant.
Yes, Siddhant. Is Dipanshu there?
Ma'am,
Dipanshu
Roshan.
Yadav?
चलो भाई 2, 3 point Dipanshu, yeah, I received
He
it,
just
but
wrote only quiz 3. He didn't mention his serial number or name.
I do not know. इसको समझा रहे हैं और ये सब ये
Excuse me,
senior
sir.
लोग हैं still. Yes.
Sir, I by mistake sent it from my Gmail, but I have again sent it from the IIT mail.
Okay. No problem. If you send it from Gmail also, that's fine. What is your serial number?
Sir, 26, Himanshu Krishna.
Hello, sir.
हाँ बोलो
Sir,
भाई.
can you check Roshan?
Have you got serial number
रोशन से
45?
पता नहीं लगता भैया. सीरियल नंबर बताओ.
Sir,
Serial number
19.
45.
19.
I got 19 and 45 both.
Okay,
चलो
ma'am.
then
Thank
it's
you.
fine. Then it's fine.
26.
Sir, can you please
26.
confirm serial 34?
Yes, 26.
34 is there, yeah.
Yes,
In fact,
34.
let Sukhvinder answer this. That is better.
So serial number 6.
Yes, yes.
Sir, serial number 38. Oh, sorry, serial number 30.
Hello?
So 39. 39, sir.
I got 39.
Okay.
Ma'am, serial number 30.
30?
Actually, hello, ma'am.
Yeah, ma'am.
Yes.
Ma'am, serial number 3.
Ma'am, actually, I
Yeah, 3. I got 3. 1 minute. Just I'm checking for 30. Yes, Pulkit Gupta.
Thank you, ma'am.
Yes.
Ma'am, 3.
Ma'am, serial
3.
number
Yes,
6.
serial. Yes, I got 3. 6. Shivam Trivedi. You are sending your second email, I think.
Yeah, ma'am. Previously was because of this figure and question was not matching. So the second I have
Okay.
sent according
If
to this.
okay, if there is any problem in your first answer, then write it down in second so that I can send that only to sir.
Ma'am, can you please
ma'am,
check
can you check
serial number
42?
16?
So we can ignore
1
his
minute. Serial
first
number
email.
16. Yes, honey.
Yes, serial number 42.
42.
By Pulkit Gupta,
Krishna.
you have written
Yes.
serial number 30. Serial number ये words में लिखने की जरूरत नहीं है. Just 30 underscore is enough.
Ma'am, can you check 41, please?
Yes, 41 Karthik.
And ma'am, I have
Payal.
not yet
1
received
minute.
my
1 minute.
last
Where
quiz.
is Payal? 1 minute. Where is Payal?
Maybe she has
Yes,
gone.
ma'am.
She didn't send. You didn't send to me your mail.
I sent to you, ma'am.
No.
What
I
is serial
didn't
number?
get your mail. Actually, sir told me that you have sent your mail to sir. That's why I'm asking. You didn't send it to
I
me.
have. Okay, I'm sending you again then.
Yeah, okay. Anyone else?
Ma'am, I was asking that I did not receive
Serial
my last answer sheet of last quiz.
Your name?
41
Your
serial. Kartik Gaur for 41 serial
What?
number.
51.
Let me check 1 minute.
Serial number 35.
1 minute. If anyone didn't receive their answer sheet, then email me. Okay. 41.
All right. All right, ma'am.
35.
Thank you.
Okay, I'll
Vijay
send
Pawan
it to
Arora.
you.
Yeah, I got.
Kartik Gaur.
Yes,
I
ma'am. Thank
have
you.
your answer sheet. Maybe by
Ma'am,
mistake
serial
I
number.
left your answer sheet.
Ma'am,
Yes.
number 50. I also didn't get quiz 2 answer sheet, and I have sent you just quiz 3 answer sheet. Please check.
Okay. Yeah, I got. I didn't send you. Okay, Srishti. Yeah, I'll write an email to me so that I can get to know that I haven't sent it to you. Okay.
Okay, ma'am. Okay, ma'am. Ma'am, did you receive quiz 3 answer sheet?
Yes. Yes, I got your.
Okay.
Ma'am.
Serial
Hello,
number
ma'am.
3.
Yes.
Click.
Yes.
Ma'am,
Serial number.
actually,
Serial number
Yes.
3.
ma'am,
Have you received my
ma'am,
email?
Yes, I got serial number 3. Yes, you speak.
Ma'am, can you
ma'am,
confirm for
ma'am, Himan, my serial number is 25. Previous one has some problem.